Good day. In this lecture video, we will be talking more about set operations. So in this lecture video, the first set operation that we will be talking about is the complements. Okay, so a complement of set A, denoted by A with superscript C or AC, is a set of elements which belongs to the universal set U, but which do not belongs to A. In other words, a complement of a set is a set wherein its elements are not found inside the original set. Elements of the complement set should be found in the universal set. Also, recall that the universal set basically contains all the elements in the universe. Thus, those elements not found in the set should be in the universal set. Also, if the universal set is defined, then that is your universal set. If it is not, then this universal set should contain uh, everything that is not inside a certain set. Okay? Okay, so complements of a set are also often denoted as A prime or A bar. Okay, so this is a formal definition of complement, which is read as the complement of A is equals to X, such that X is an element of a universal set, wherein X is not an element of A. So if we show visually using a Venn diagram, this is what it looks like, wherein the shaded part is the complement of set A. So here is an example. So given these two sets, so the set U, which is our universal set, with elements X such that X are all fruits in the planet. So as you can see here, the universal set is defined. So this is what the universal set should only contain. So this set only contains the fruits, okay? All the fruits in the planet. Now, okay, so now that, okay, so now we have another set, which is the set A. So here, the set A only contains those fruits that are color orange. Now, what do you think is the complement of A? So basically, the complement of A is those fruits that is not color orange, since this set only contains fruits that are color orange. So that means that elements or fruits that is not color orange should not be in this set. So basically that is the complement of the set. So all the fruits that is not color orange is now a member of the A complement. Okay, so that is complements. Now let's proceed to differences. So differences is also called as relative complement. Okay, so the difference of A and B, denoted by A slash B, is the set of elements which belongs to A but which do not belongs to B. So it's just basically the difference, or we remove the elements found in B and A from A. Okay, so here we see that A minus B is equals to X, such as this X is an element of A, but this X is not an element of B. So if we show that visually using a Venn diagram, this is what it looks like. So only those elements found in A is uh, is the solution to this operation. So you can see, though this part here is also belongs to A, since this also belongs to B, we deducted it or we minused it. So we removed it from the solution. Okay, now here is an example. So we have set A and set B. Okay, so our set A 1, 2, 3, 4, 5, and our set B 2, 4, 6, 8, 10. What do you think is A minus B? So A minus B are just those elements unique, also only unique to A. Okay, since 3, 4. Since 2, 4 is found in B, so we removed it. And we only have 1, 3, and 5 since this is the only elements that B does not have. So that is the solution of A minus B. Now what if B minus A? So basically it's just the same. We just deduct or remove elements found in A in B. Okay? So we have 6, 8, 10. Since 6 is not found in A, 8 is not found in A, and 10 is not found in A, so that is the solution for B minus A. Okay, so the next we'll be talking about the symmetric difference. So symmetric difference of sets A and B denoted by A, this one cross B, consists of those elements which belongs to A or B, but not to both. Okay, so not the intersection of both A and B. So it is written in this equation. So more formally, the symmetric difference of A and B is equal to the difference between the union of A and B and the intersection of A and B. Or the symmetric difference of A and B is equals to the union of the difference A and B and the difference of B and A. If we visualize the symmetric difference using Venn diagram, it will look like this. So as you can see, only the elements that is not in the intersection of the set A and B is what the symmetric difference will acquire. So basically, symmetric difference are those values unique to A and set B only, not including the intersection. So here is an example. So we have these two sets and we are asked to find the symmetric difference of A and B. So now recall that the symmetric difference is equivalent to these forms. Now let's try this first form. Okay. Now using this first form, we have this one. So we have this as our resulting set. Okay. Now if we try the second one, okay, so this is it. So this is the resulting set of this one. Now if we try this one, we have this. So as you can see, the results are the same. So, so these elements, the answer, should be the elements only unique to A and B, but not their intersection. So we have this one as our final set. Note that when it is your time to perform this operation, you don't have to use these two definitions to get the result. You may use one of them since both definitions will always yield to the same answer. However, you can always just find those elements from A and B that is unique to A and B alone, and not in the intersection of A and B. Here we see the encircled elements are common to both sets. Thus, the remaining elements should be the symmetric difference of A and B. See? So the circled ones are the common elements from A and B, and the squared ones are those elements that is not common to both sets. So this is what the symmetric difference acquire. Now, last is that the fundamental products. So in fundamental products, we consider n distinct sets A sub 1 to A sub n. A fundamental product of a set is a set of the form this one. Okay, so it is the intersection of all of these sets where each of the A sets or each of these sets could be the original set or it could be the complement of the set. Okay, so it is quite complicated to see what fundamental product is only by looking at this definition. So here is an example. So suppose we have sets A and B. So their fundamental products should be the union, should be what you call this? Kanang combination bitaw. Combination bali sa tanan operation na mabuhat nimo through intersection and the complement of that set. So we see here that A intersection B, and also the A complement is intersected to B, and the A is intersected to B complement, and A complement is intersected to B complement. Okay, so as you can see, all of the possible combination of the sets A and its complement with the intersection is here in the fundamental product. And we have four fundamental products from these two sets. So basically, we note that there are m, no, is equals to 2 to the n fundamental product wherein n is the number of sets involved. As you can see here, we have two sets involved, A and B. So meaning we have four fundamental products since we have 2 to the 2, since we have two sets. So we have four fundamental products there. So if we, for example, we have three sets, then this should be 2 to the 3. So this should be 8. So there should be 8 fundamental products when it comes to finding the fundamental products of three sets. Okay, so this is the example I just gave to you. So it has four fundamental products since we have two sets. So 2 to the 2 is 4. So we have four fundamental products. Okay, so any two such fundamental products are disjoint, meaning that all of this should not have any intersection or should not have any common element. So P1 and should have no common elements with P2, P3, P4, and the rest. Okay? And a final note is that the universal set U is the union of all these fundamental products. Okay, so if we union all this fundamental product we acquire, this should contain all the elements in the set U. Okay, so here is an example. So we are given three sets, set A, B, and C, and our task is to find their fundamental product. Since we have three sets, then we let n is equals to 3, thus we have 8. So we have 8 fundamental products. And these are the 8 fundamental products that we have. So this is um, composed of the sets itself and the complement of set as well as operation intersection. So if we draw this one in a Venn diagram, we will have this. So as you can see, all the fundamental products is disjoint, and all of these fundamental products when unioned should be the elements of the set U. So that is what the fundamental product does. So that is all for our set operations. So in this lecture video, we talk about complements, differences, and symmetric differences, as well as fundamental products. So I hope you learned something new, and see you on the next lecture video.